Now, here we are ready to start with section 2. We have a slightly different learning goal, and in this specific section, what we're going to actually talk about is what are the factors that are going to affect our reaction rate. Now, the whole purpose of this is we need to go back and look at what's called the collision theory. Here are the main points, the main highlights. 1, first, the reacting species, they must collide with each other. Second, they must be oriented or arranged in such a way so that the products or the two reactants can come into contact and make the bonds that are necessary. And last but not least, and this is the most crucial point, they must have enough energy in order to make a change. What do I mean? If you remember last year, we took some time and talked about activation energy, or our EA. What we're looking at here is the minimum amount of energy, the least amount of energy that we can utilize in order to get the reaction started. Now, in a slower reaction, we're going to notice that it must be a larger activation energy. If it's a very fast reaction, there's most likely a very low activation energy, and that could be based on the species that are reacting, or that could be on the presence of a catalyst. But we're going to take a little bit of time. We're going to look at 4 factors that can be affected just by the actual substance themselves, and then we're going to add on the last one, which we can add something else into the system that's going to allow the reaction to speed up. Now, the first thing that we're going to look at is we're going to look at the nature of the reacting substances. If we're dealing with things that are in an ionic form, most likely they're going to react much faster because of the attraction of those ions. But when we look at larger compounds, we tend to notice that they are much slower. The reaction happens much slower because there are many bonds that need to be broken and the amount of time that it takes. Now, the third factor that we're going to look at here is if we have maybe a smaller compound that has a lot of strong bonds in it. What do I mean? If I was to use acetylene for an example, acetylene has a triple bond right there in the middle, and so there's a lot of energy stored in that bond. And so I'd have to put in a lot of energy in order to break it. But once that bond is broken, it would also release a lot of energy. A main example that we can use here, or a couple that we can use, the oxidation of methane, which is very, very fast. The bond energies are very, very small, and the molecule itself is very small, versus photosynthesis, which is very slow, and we have the breaking down of and formation of glucose molecules, the double bonds being formed, and so forth. The second part that we're going to look at is the size of the particles. Just like any other system, the smaller I make it, the better or easier it is in order to react. If I have a big block of salt and I put it in water, it'll dissolve over time. But it may take maybe an hour or longer depending on the size of the block. If I crush it down into a powder, just like from a salt shaker, and add that to water, it's actually going to break down much, much faster. The water molecules can actually get in closer and pull more of those ionic substances apart and break them down so that we end up with an aqueous solution of sodium and chloride ions. Now, example used here also, if we look at coal dust, and I like setting things on fire, and so this was why this one sort of came to my mind. If I have a lump of coal and I try to heat it, it's going to take a long time for it to catch and to retain that heat for a reaction to start. But if I take that same lump of coal and grind it down into a fine, fine powder, I get a very, very reactive, very explosive reaction or burning. This is what we want to do in order to increase our reaction rate. Now, the third thing that we can utilize here is the temperature. Depending on the temperature, some reactions will happen faster than others. If I'm looking at a general reaction of at 10 degrees Celsius, I will have the reaction many times go through to completion. But as each degree that I raise that temperature, will be more energy that is transferred to those particles. The more particles, the more that the particles are moving and the faster that they're moving, the better chance for those collisions, the more collisions, and the better chance we're going to reach that activation energy that we need. This is going to be a great factor and a great help, actually, as we continue to go through. The fourth thing that we can do using just the substances and the reactants is we can look at the overall concentration. If I add more of the substance into the beaker, into the container, that's also going to increase my chances. Just a general idea that you can use. If I have a large parking lot with only 10 cars in it, it's very unlikely that I'll actually have a car accident or any issues. But if I take that same large parking lot and fill it with cars until there are only a few spaces left, I have a higher chance of having a car accident or something happen. In the same way, the more particles that I can put into our solution, the better the chance I'll get my reaction and the better chance it'll be for my product. Now, the last thing that we're going to deal with, and as I said, I kept this one separate because it's me adding in something that is not originally a part of the equation or of the reaction, is using a catalyst. I like using these, or using the examples of many times we deal with enzymes that catalyze reactions within our body. Now, the great thing about this is catalysts increase the reaction rate, but in the end, they're actually not consumed. So if I'm using platinum as my catalyst, it's a very expensive metal, but once I buy it, it does not break down. It does not react. So I can have and use that catalyst over and over and over. Now, how does it actually speed it up? What it's going to do is it's going to provide an alternate mechanism with a lowered activation energy. So if I needed originally 1,500 kilojoules of energy in order to get the reaction started, what I can do is, by using this catalyst, I may now only have to go up to 900 kilojoules of energy that are necessary. This is going to allow a larger fraction to actually make it into that product form, which is what I actually need. If I'm in business, that's my goal. How can I get the best product and the best way, the fastest, and even the cheapest? Example that we use constantly is looking at the decomposition of hydrogen peroxide. When we add to it manganese dioxide, we notice that it begins to speed up, it bubbles, and it releases oxygen. Now, this is just a little bit more information about the catalyst, because we're going to be using this as sort of a guide or a framework. Before, when we wrote our equations, we would always look at the beginning and just the end products. So here I have nitrogen dioxide and carbon monoxide reacting. Through this reaction and through their interaction, they're actually attracted to each other. The bonds are sort of stretched and twisted and turned, which weakens them and allows it and makes it much easier for them to react with each other. In our final setting, we get that we have nitrogen monoxide and carbon dioxide. But this section here in the middle is where we actually want to pay a little bit of attention. This point of bonding right here. So this oxygen has actually been drawn away from our nitrogen dioxide. And then because it is drawn away, those bonds are weakened. That energy that is able to be put out by carbon actually makes a difference and is actually able to pull that oxygen away to form a new compound. This thing that's been formed here in the middle is called a transition state or activated complex. To give you an idea of what it really looks like, if you remember our potential energy diagrams that we used last year, many times they looked like this. What actually happens many times is, as we have our potential energy diagram, it may actually look like this. This being our transition state or activated complex. Now, last but not least, back to our old friend, the potential energy diagram or energy profile diagram. Now, you need to know both of these terms interchangeably because they will come a point where you will see both of them on the test. Remember how to calculate each part. And in the end, also remember, you're doing all of your calculations in terms of kilojoules or joules. Make sure that you can calculate and know that I'm looking at the difference between where I start and where I finish. That's going to be, like we had before, this is going to be our delta H. This is going to be our delta H value that we talked about before. Our main concern here is actually going to be now, what happens if I add in a catalyst? How will that affect my overall pattern? Now, tomorrow when you come into class, we're going to take a little bit of time. We're going to go through those examples. Please, please, please make sure you took notes. If you have any questions, write them down so I'll be able to answer them as best as possible. Have a good evening, and I look forward to seeing you in class tomorrow.